Second. Okay. All right. So we are recording right now. All right. I just really quickly before I started here, I wrote a couple more RNA, mRNA sequences here for us to kind of reinforce those topics within chapter 11, nucleic acids, how we are able to use the genetic code and the ordering of the nucleotides within a DNA strand or an mRNA strand to get the ordering of peptides that form when our DNA is giving the instructions to build the proteins that build our bodies. So I just have a couple more examples right here. I stole them from the book. And so do know with a question like this, if I give you an mRNA strand or a DNA template strand, how we go about using the genetic code. In order to use this genetic code, we need to be looking at the mRNA strand, or messenger RNA strand. That's the copy, the photocopy of the instruction manual to build the polypeptide strand. So it's important here that you're looking at the 3-letter codon for an mRNA strand. Also, make sure that when you're reading the mRNA strand, it orders from the 5 end to the 3 end. So in this first example that I have right here, I give it to you exactly how you would read off of the genetic code. It's the mRNA strand and it goes 5 to 3. So my strategy here is to just kind of group them in 3 letter chunks to give us each codon so we can determine what is the order of the amino acid sequence that would be produced given this mRNA strand. That's how the question would be like worded on an exam. So you will be given this exact genetic code. So do know how to read this wheel. All right, so let's do this one. So AUG, I'm pretty sure that that's the start codon. Yep, so AUG, so the first amino acid here would be methionine. All right, methionine. Next, UAC. So UAC be tyrosine. GGU. So GGU, that's glycine. GGA, so GGA, glycine again. So do note that some of these amino acids, because we have less, like there's 20 that we have within our bodies, 10 of which are essential nutrients, meaning that our bodies cannot create them. But there's many more combinations of lettered codons. So you can see some duplicates here, such as glycine. There's a bunch of different combinations that still give glycine. All right, so we did GGA and now UUU. So UUU, phenylalanine. So that would be the amino acid sequence. So do make sure you're reading the mRNA strand, reading 5 to 3. So another way I could ask the same question is not just giving you straight up the mRNA strand, but I can give you the DNA template strand. So recognize that DNA lives within the nucleus of the cell. That's not where protein synthesis occurs. Protein synthesis happens on the ribosome, which is outside the nucleus in, the main portion of the cell in the ribosomes with your ribosomal RNA. So your DNA template has to interact with your mRNA strand to give that complementary strand. So our strategy here, given the DNA template, the transfer RNA doesn't read the DNA template. It has to read the complementary mRNA. So we need to make the mRNA strand that would result from complementing this DNA template. So do note that when you are looking at complementary strands, the complementary strand orders the numbers reverse. So here the template is 3 to 5. So this will make our mRNA strand start at 5 and end at 3. And now these letterings we can use to get the complementary strand, right? Our rules here, A equals T, but when it's RNA, it's U. Then what's G equals C. So we make sure that we get our complementary strand here. So C would be G, so 2 G's, C, C. A, it would not be T, it would be U in this case, and then 2 T's would give an A, or AA, sorry. So do note how that works there. If A is in your DNA template, then you get U, but if you have T in your DNA strand, your DNA template, you will get A, because T exists in DNA while U is the complementary, or like the same, kind of replaces T within your mRNA strand. And then the last two here, CAG, that would be GU C. There we go. All right, so that's not our answer. That's just the complementary mRNA strand. So now this question it mirrors exactly how the previous one is. We group the 3-letter codons here and go to town with our genetic code. So GCC. Hopefully I got that right. No one's calling me out that I'm wrong in the chat, so that's good. So GCC, let me delete all this. Okay, it's GCC, so alanine, UAA, so UA, oh crap, it's a stop codon. Whoops. Sorry, I just made this one up. We shouldn't be stopping in the middle here, but just point to the whatever actual amino acids it's pointing at, and then GUC, which would be, sorry, I made this up on the spot. I thought they were all good. So GU and C, it would be valine. Did I get that one right? ATT. So A is U, TT is A, yeah, U. Yeah. Okay. Sorry about that. I had to stop in the middle there, but that's the process that you would go. So if this was an actual mRNA strand, the mRNA, your transfer RNA would stop right here. So all that would be on your strand would be alanine. So that's what would actually happen in your cells in your body, but do recognize when it's asked as a question like this that you will actually get real amino acids when doing the 3-letter codons. All right. Okay. Do you write stop? Just know if there's a stop codon in the middle because I made a bad example. Do know that there won't be a stop codon in the middle of your template on the exam. All right. So. And if you do get a stop codon in the middle, then you probably did something wrong. Yeah, all right. Okay, so what chapter do we want to go with? Is there a certain section we want to do? Anyone? Write it up in the chat. So we kind of worked backwards here. Chapter 1. Okay, so all right, let's just start at the beginning. Okay, so we did a lot of the end, so let's just go all the way back to the beginning. Did we do this part? Did we do here? Did we do these ones? Density of gold, did we do that one? Yes, okay, good. All right, we did these ones, drip rates. Wait, did we do drip rates in class? Yeah, we did. Yes. Okay, all right, so we did those ones in class. So if you're wondering about some of these ones that we don't cover today, do just go back to, there's another video posted under the Zoom link. We stopped at question 9, perfect, thank you. And you'll get those questions there. I posted the questions that we did in class on that Zoom page. So you have the rest of those questions, all right? Okay, all right, so we stopped at 9. So we'll just keep going, I guess, with 9 here. So this is chapter 2, where we talked about atoms and atoms and the subatomic particles within atoms, right? And then kind of extending on that, we talked about different types of radiation, because a lot of you are going on to radiology. And so it's important to understand how radiation affects our bodies. Alpha particles are not so bad when alpha particles are penetrating from the outside of our bodies. So like smoke detectors are emitting alpha particles all the time. It's not so dangerous because the alpha particles, they just hit our bodies and they're actually stopped by just clothing. But what is really bad is if you have alpha particle emission inside your body, where there is no barriers, that if you essentially have a really, really big helium nucleus just bombarding your cells, and that can be really dangerous when it's inside your body. And that's the whole basis of the movie and the book Radium Girls, that these girls were ingesting radium and they were alpha emitters. And so, but it was inside their body. That's why it was really bad. All right. So in number 9, we're looking at different types of radiation. We talked about alpha, beta, and gamma. So do understand the mass numbers associated, the different numbers associated with these different types of radiation, because it helps us when we're balancing these equations. We'll be able to figure out what's the missing piece. So you see right here, this helium nucleus, this is your alpha particle. All right. So an alpha particle is a helium nucleus where it has 2 protons and 2 neutrons. It's basically a helium 2+ because there are no electrons, but typically it's written like this. And so how we approach questions like this is recognize, okay, these symbols, uranium, how we kind of look at these isotopic symbols here is that top number in the superscript tells us our mass number. This mass number is the number of protons plus the number of neutrons. While down here, though I don't have a number written, this is typically where you have the number of protons on your atom. And so typically when you see isotope or atom symbols like this, you don't see the number of protons, because we are given the elements. So we know how many protons there are. It's kind of assumed. So if you take your periodic table, which you'll always have on the exam, though there won't be any names, uranium is atomic number 92. So that means there's 92 electrons. And so from there, we know how many neutrons there are. So this could be another question, right? If we wanted to, I could say, you know, how many protons, neutrons, and electrons are on a neutral uranium atom? Why don't we just do that? All right, why don't we just do that? So 235 uranium. So let's figure out how many protons, neutrons, and electrons are on this atom. So we already said that the identity of your atom tells you the number of protons. So there are 92. And so the number of neutrons comes from the mass number. There's 3 different equations that, and I'll write that there, how we get all these different subatomic particles. Your atomic number is your number of protons. So you have to identify, you know, what element it is, and you'll know from its atomic number how many protons there are. Then it's the mass number. All right, and so that's the larger number up here in the corner. This number is equal to the number of protons plus the number of neutrons that are in your nucleus. So from this, if we take 235 minus 92, so this is 235 minus 92, there will be, okay, I didn't actually do this. Oh, the next question actually has more of this practice, but you know, more practice never hurt anyone. There's 143 neutrons there. And since this is a neutral atom, I know it's neutral because there's no charge. If there was a charge there, then we would use our last equation where charge of your atom or particle, ion in this case, is the number of protons minus the number of electrons that are there. So remember, protons are positively charged, electrons are negatively charged. So since this is a neutral atom, the number of electrons is just the same, 92. All right, and so we'll do more practice on the next question. Oh, on my key. So hopefully, I guess I'll throw it up in the chat. But you know, you have access to these on Carmen. The key has those 3 equations that I just wrote here, and that will get you through any like, you know, figure out the number of protons, neutrons, and electrons on an atom. Okay, let's actually do number 9. Sorry about that. Okay, so, but it is important that we know, based upon the mass numbers that are given, the number of protons, we can figure out what's the missing piece, right? So NP, that is neptunium, though that's not a name that you have to memorize, but you should know from NP, you know, find it on the periodic table. We see that that is a atomic number of 93, so 93 protons. So now we need to figure out the missing piece here to make everything balanced. So what I look at here is, okay, your mass numbers are the exact same. So the missing piece will have 0 mass, but the number of protons are different. And so in order for those to be balanced, there needs to be a -1 within there. So you can see like -1 plus 93 is equal to 92. So the missing piece is a beta particle within there, or sometimes it just has an E, but this is a beta particle, right? So you see that with emission of a beta particle, the identity of your element actually changes. It goes up a mass number within there, because basically what's happening is that a neutron is losing an electron and becoming a proton. And so that's essentially what beta emission is. What would you word this as? You emitting a beta particle? Yes, that's how I would word it, because the word emit means that something is produced. So the particle that's being emitted is being produced, so it's a product. Does that make sense? So if something's absorbed, then that would be a reactant, because the two things are combining. But since it's emitting, your particle, your radiation here is a product. So that's a great question. Yeah. So there's other ways I can word it that isn't just, like complete the chemical reaction. In some of the overview sheets, I use words like emit or absorbed to tell you, okay, the particle is on what side of the equation. Great question. Okay, so the next one here, same idea. So we already said uranium is 92. So we just need to figure out what's the missing piece. So I see our helium atom has a mass number of 4. 234 is uranium, so this would be 230 would be the mass number. And then 92, 2 on the other side, so this would be would have to have 90 protons in order to make all of that balanced. And so we're not done. We need to identify what element it is. And since we identified that it is 90 protons, so this would be thorium based upon the periodic table. All right. Okay. Last one here, and this is the last particle. And so your helium nucleus here, that's an alpha particle. This last one, we see that the mass numbers are the exact same. We just have a little m within there, but the element is the same too. So we see that, the substance isn't really changing. So this radiation that's being emitted is just gamma radiation. It's just pure energy. And so what that M means is metastable. It's not super stable. So all it does is just emit energy within there. So we see that even if we use the same rules here, if we look at the mass numbers, okay, that is equal, or equal on both sides, and so is the mass, the number of protons. I didn't actually write it down. There's 91 protons. So we see that that's all equal too. So that's gamma radiation. It's the most penetrating because there's no mass. It's just pure energy within there. Okay, so that's number 9. The big idea here is being able to balance. All right, let's do number 10. So do you know the strategy that I have on the key, those 3 equations to help you navigate these? So the first 2 that you see here are neutral. So you can see that the number of protons will be equal to the number of electrons, but not for the last 2. So we'll just do these 2 because it does have a charge. And so I give you the elements here. So you should be able to identify that the number of protons are just related to what element it is. Fluorine, there's 9 protons. For calcium, there is 20 protons, right? And so from there, we can get neutrons from the subtracting from the mass number. It's all the leftover mass within there. So for our fluorine example, there's a mass number of 19, so -9 is 10. And for calcium, this calcium example, there would be 20. Because 20 plus 20 is 40. And then the number of electrons here, don't always assume that the number of electrons is equal to number of protons. That's only for neutral atoms. These 2 are not neutral. So I like to see, okay, this fluorine or fluoride particle is a negative charge. So I like to think, oh, there's an extra electron that has to be there to be negative. So there's 10 electrons, but you can also use the equation on that the key, that the charge of the thing that you're looking at is equal to the number of protons minus number of electrons, and you'll get the same answer, where it would be -1 equals, we already got 9 minus X, or number of electrons, so you can see X is 10 here. And then for calcium, it's a 2+ cation, so I like to think there's 2 less electrons there to balance out the protons, so there's 18. All right. Okay, so can we go over chapters 4 through 6? We'll probably get there. So let's just go in order here. There's just a little bit more to do. We'll probably get to 4 and 6. All right, so the next one here. So the idea here is like for fluoride and the calcium ions, those are typical charges of fluorine and calcium, where we can predict the charges of elements when they are ions based upon their group number. Fluorine, we know, typically makes a -1 anion because it's in group 7. It typically gains 1 electron to get a noble gas configuration. Same with any group 7 element. Fluorine, chlorine, bromine, all of them typically make -1 anions, versus calcium is a group 2 element, so it typically loses 2 electrons to achieve its noble gas configuration. So we can kind of take advantage of that idea that we can easily predict a lot of the main group elements. And what I mean by main group elements, I mean groups 1, 2, 3, 4, 5, 6, and 7. Those are our main group elements that we can easily predict the charge most of the time. So in question 11, it says, okay, what group number element is this substance given this formula? So inspecting this, I can tell right off the bat it's an ionic compound. It's attached to SO4, which we call sulfate. All right, so remember, that is something you need to memorize, your polyatomics, the charge, the formula, and the name, because that's related to naming within there. So this is sulfate, and typically sulfate is SO4 2-. So this will help us out because we know that this whole substance is charge neutral. So I see, okay, there's 3 sulfates here. Each sulfate is a -2 charge. So since there's 3 of them, there's a total of a -6 charge coming from anions. So I see our X component here has to balance that out so everything's neutral. And there's 2 of them. So I think, okay, 2 times what equals +6, because we need the cations to equal out to neutral, or not neutralize, but to even out the negative charge within there. So I know X has to be a charge of +3. All right. And so then if you kind of put all of those pieces together, if we have 2 +3s, that's a +6. That will equal the -6 charge coming from the 3 different sulfates. So +3 isn't our answer. This question is asking what element and what group number would typically have a +3 charge. And so what we learn here with cations, typically the charge is its group number. So the answer would be C in this case, that a group 3 element like aluminum will lose 3 electrons, so it will achieve a +3 charge within there. So that is the answer. Or this question could have something like aluminum, calcium, sodium, oxygen, bromine, or something like that. And I could ask, okay, what is the identity of X in this formula? And the answer would still be the same. We would pick aluminum because aluminum is a group 3A element. It typically loses 3 electrons. Okay, so there we go. So let's do a little bit of naming. All right, so given formulas, name them. And so there's 2 schools of thought. Is it ionic? Use ionic naming rules. If it's ionic, look at the metal. If the metal cation is a charge that you can easily predict, you don't need a a Roman numeral, but if it's a transition metal or a metal that you can't really predict the charge as much, you need to use the stock system and indicate what charge it is. And do know that you can predict charges based upon the anion that's present. That's if you have a metal and a non-metal, or polyatomic ions present. But you can also have a substance that's all non-metals, and that would be under molecular naming rules, where you actually have to say how many of each element are present. So I see here BRCl, those are two non-metals. All right. And so you see my strategy on the key, figure out, is it molecular or ionic? So I see that BRCl, all non-metals. So that's molecular. I use molecular naming rules. I just name the elements there and say how many there are. So this would be bromine. So if it's just one of the first element, you don't have to say mono. But since there's one chlorine in the second element, you do have to say monochloride. All right. And so the reason we have to say the number of things that are, or elements that are here in these molecular compounds is because you can't predict charges. There are no ions in molecular compounds. I always like to show the example like NO2 versus like NO, or no, that's not a good example. What if we do like SO2 and SO3? Some students will say, oh yeah, that's sulfur oxide or something. Right? You name the first element, you name the second element, but how can you know how many oxygens you have if you just call it sulfur oxide? You have to say how many oxygens there are. So this would be sulfur dioxide. This would be sulfur trioxide. We have to say how many of each there are, because charges aren't as predictable like they are in ionic compounds. So the next one is ionic. I see that this is iron. I like ionic because you just name metal, anion. And this second substance is acetate. It's one of the polyatomics to memorize. And I know acetate is a -1 charge. It's basically the carboxylate version of acetic acid, if you have caught on to that. So that's acetate. And so since our anion charges are always very predictable, whether it's a non-metal or a polyatomic, I can figure out what the charge of iron is based upon how many anions I have. I know that iron has to be +2 in order for this to be charge neutral. So I'm going to call this iron 2 acetate. All right, I have to say it's iron 2 because iron isn't a typical metal that you can easily predict the charge. Sometimes iron is 2+, sometimes it's 3+. Basically, the rule is that most of the transition metals, unless it's zinc or silver, you have to use Roman numerals. That's basically it. Okay. All right. And then the last one here, calcium hydroxide. Oh, I guess I already said it, but same idea. This is ionic. You name the metal and then the non-metal, but in this case, it's a polyatomic anion. OH in a ionic compound is called hydroxide. OH, when it's in a molecule, we usually call it that in an alcohol group. So this is different. OH is a hydroxide. It's basic. It's a base. So yeah, we just name the metal. So this is calcium. And then OH would be hydroxide. We don't have to say how many there are because both of these substances, what the charges are of them. Calcium as an ion is always 2+. Hydroxide is always -1. So if you are given calcium hydroxide, you know how to make that charge neutral. And so we'll read that down here, some of these ones. And again, the same idea. Is it molecular or naming or ionic naming? So sulfur tetrafluoride. So since it's telling me how many there are, I know this is molecular. So sulfur fluoride is F. So there's tetra. So that means there's 4 of them. So that's identifying that is molecular. The next one, yttrium sulfate. So I like to just identify, okay, what's the cation? What's the anion? So sulfate is SO4 2-. And yttrium, see, there's a Roman numeral. I love Roman numerals because you don't even have to think about what the charge is. It tells you what it is. It's yttrium 3+. Perfect. So now it's just up to us to combine those and put the right subscripts so you get a charge neutral substance. So this would be Y, 2 of them, and sulfate, put all of that in parentheses, there would be 3 of them. So we see if you kind of just make the charges, the subscripts in your neutral balanced chemical formula within there. All right, and the last one, lithium nitrate. So again, identify your ions. So lithium as an ion is lithium plus, because lithium is a 1A element, and nitrate is NO3 minus. And then you just make sure that everything's charge balanced. So it'd be Li NO3. There you go. All right, so let's keep going. All right, so drawing Lewis structures. Did you guys know that there was a cow on campus? Did you hear that there was a cow on the oval? Did anyone see it? I had students emailing me that there was a cow. I think they thought that would interest me. And they were right, it did. It gave birth? What? Are you sure it gave birth? Or is that just like, no, okay, apparently that was a lie. Oh no, it just peed. Okay, I can see that how that can be confusing. Wait, Yik Yak? I thought Yik Yak went away. I used to go on there a lot. I thought it was funny, but I thought it went away. No, it came back? Cool. Maybe I should go back on it. You guys are funny. Okay, Lewis structures. All right, so Lewis structures is based upon molecules, small molecules, so not our big organic molecules, though there are some similar concepts that come back within there. So Lewis structures, can we draw the Lewis structures of these different substances? So I have 6 steps that we go through, so just memorize those 6 steps. The first one is count the number of valence electrons here. So since there's 2 hydrogens and an oxygen, 2 times 1 electron on hydrogen, 6 electrons on oxygen, we are allowed to place 8 valence electrons here. So the next step is to get your skeleton structure. So oxygen's going to be in the middle because hydrogen can never be a central atom. And then we need to make sure that our structure has 8 electrons. So remember, bonds always hold 2 electrons. So I've already drawn 2 bonds. Everything needs to be bonded. I've already drawn 2 bonds. So if I spent 4 electrons, I still have to spend 4 more. And so I will put that on the central atom and ensure I complete octets. So this is the Lewis structure for water. I hope when you think about water, you think about this Lewis structure. Hopefully it comes to you pretty quickly that oxygen has 2 bonds to hydrogen and 2 lone pairs. I feel like we draw water, and work with water a lot. All right. So yeah, there's water. We have the Lewis structure. What is molecular geometry? So here's where we count the number of bonds and lone pairs, and that can tell us what the molecular geometry is. There's 2 bonds and 2 lone pairs. So that's a total of 4 electron clouds. So the electron geometry would be tetrahedral. If we looked at all of the electrons, it would be a tetrahedral where all the bond angles are 109.5. But 2 of those electron clouds are electrons, lone pairs. We can't see electrons. So when we describe the molecular geometry, we're only looking at the atoms. I like to tell students, literally erase the lone pairs and tell me what shape is that. So if you erase the lone pairs on your electron geometry, that will tell you the molecular shape. So water is bent in this case. All right. So yeah, it's bent. That is the molecular geometry. This would be polar, because if you have that bent shape, those hydrogens are pulling on that oxygen unevenly, that those bonds don't cancel out at all. It doesn't even matter what the bond polarity is, they'll never cancel out because they're in that bent shape. They have to be like across from one another in order to cancel out. So it's polar, and we know water is polar. And so I like to use my analogy, my babies and bodybuilders analogy. If they're all pulling in the geometry, pulling on that central atom, does the central atom move at all? And if it does, it's a polar molecule. So in this case, since the hydrogens are kind of congregated on one side, it'll be polar. And then we want to state what the approximate bond angles are. So this is where we have to kind of look back at the electron geometry. The electron geometry is tetrahedral. The bond angle there is 109.5 for a perfect tetrahedron. But because there's lone pairs present, your actual bond angle here, lone pairs are really big and fluffy, so it'll actually be slightly less than 109.5. I think water has a bond angle of like 104 or something like that, all right, degrees. So that's the bond angle within there. So it just deviates slightly under from your perfect tetrahedral. So the question was, does bent fit under tetrahedral? Yes, it does. So you can think of your tetrahedral as your parent structure. If you had 4 electron clouds, they were all the same, it would be tetrahedral. But since 2 of them are lone pairs, electrons, and we can't see electrons, I like to just cover up what those 2 electrons would be in your tetrahedral, and that's your actual molecular shape when you are only looking at atoms. All right. So I think like CCl4, if you draw CCl4, if we quickly do that, you'll get that you have carbon in the middle with 4 chlorine bonds around, and all those chlorines have fulfilled octets. So this structure actually looks just like methane. It looks just like CH4, but there's more electrons because chlorine just has more electrons. This would be a perfect tetrahedral where the bond angles are exactly 109.5 because there's no unevenness, there's no lone pairs taking up more space. Everything is taking up space equally. They're all identical in this case. So when you draw this CCl4, and it's a tetrahedral, right? You can draw your molecular geometry, all of those bonds are chlorines within there. So since all of the bonds are 109.5 away from one another, they're all equally spaced in space. It's not flat like this. This molecule is not flat. It actually looks like 3-dimensional here, a tetrahedron. This would be a non-polar molecule because all those chlorines are pulling on it equally. All right. Okay. And so the last one here, CH2O, where carbon is the central atom. So this is formaldehyde. All right. It's a aldehyde. And I'll show you. It'll look like the functional group aldehyde. So let's go through the same steps. So for that last one, I kind of skipped steps, but you can get to it and count how many electrons are there. So we have a carbon, we have 2 hydrogens and an oxygen. So that's 4. 2 times 1 and 6. So there's a total of 12 valence electrons we can spend. I told you that carbon is the central atom, and we have 2 hydrogens and an oxygen. So that's my skeleton structure. And I just see, okay, I drew 3 bonds, so I spent 6 electrons already. Now I have to place my leftover electrons on outer atoms first and fulfill octets. So I have 6. So I'm going to put the next electron on oxygen because it's an outer atom. So 6, 7, 8, 9, 10, 11, 12. I spent all the money I have, or all the electrons that I have. So the next step here is you check octets. So hydrogen's fine with just 1 bond. Oxygen has 1, 2, 3, 4, 8 electrons, but see, carbon here does not have enough. So this is a problem. This is where we need to start drawing double bonds to carbon so it can have a fulfilled octet. So how we do that is we take electrons off of an outer atom and we draw it instead. So we're just moving electrons. We're not adding more electrons. We're just moving around the ones that we have. So I'm going to move that lone pair on oxygen in between carbon and oxygen instead. So there's a double bond there. So do keep track of the electrons that are left over. So there's still 2 lone pairs on oxygen, and then we have hydrogen and hydrogen there. So if you count, there's 12 electrons. Everything has fulfilled octet. This is the Lewis structure for formaldehyde. And so what you see here, this is an aldehyde. Look at the, this is chapter 4, I guess. Whoops, how did I do that? We have oxygen and carbon double bonded. There's our carbonyl. And then we have a hydrogen attached to that carbonyl carbon. So this is an aldehyde. All right. Okay, so there's my Lewis structure. And so we need to figure out, okay, what is the geometry? So there are 3 electron clouds. So this would be trigonal planar. All right. So I did not draw the Lewis structure of how it would actually look like. This molecule would actually be trigonal planar about 120 degrees from one another. If I wanted to draw the Lewis structure more correct, it would actually look like this. And that's typically how we draw aldehydes. In that case. All right. So if this was a perfect trigonal planar, it would be exactly 120 degrees, all of those bond angles. But because there's a double bond here, it pushes this hydrogen-carbon-hydrogen bond a little bit smaller. So this bond will be slightly less than 120 degrees. And these 2 bonds up here that are adjacent to the carbonyl will be slightly more than 120 degrees, just because that double bond kind of deviates the perfect trigonal planar 120 degree geometry within there. All right, so that's how you do Lewis structures. Okay, and we'll see, you know, these shapes they make their way through when we get to organic chemistry. All right. So let's do a little bit of math. Yeah, see, we're almost at chapter 4. See, let's just be patient. Okay, so a little bit more math. So we talked about atoms, all right? And the thing is, in lab, we never work with just an atom. That's impossible to do. We are really big human beings, and we always work with a lot of atoms at one time. So we need to think about them on a scale that we can actually weigh, thinking about them in terms of grams. So we have to consider, what's the question? The question is, so what is the overall bond angle since some are greater than 20 and less? In a question, I would have to specify what bond angle I'm talking about. So I would never say like, what is the bond angle here? Because there's different bond angles present. Different bond angles present. So I'd have to specify what is the bond angle of hydrogen carbon to hydrogen, for example. But note, like in our water example, there's really only one bond angle to worry about. So what you see here, that's all hydrogen, oxygen, hydrogen. So it's 104. So we just kind of talk about one. But like, let's say I was working with NH3 ammonia. So you hopefully can see the trend here. We have you know, two lone pairs. Ammonia, if you draw the Lewis structure, looks like this: 3 bonds, but only 1 lone pair. It's not flat. It's a tetrahedron, but it's missing one of its legs because one of its legs is a lone pair. So it's actually a trigonal pyramid, right? It's just like 3 feet there. So if we kind of draw a tetrahedron and just recognize, okay, one of those is a lone pair, and it's pushing the bond angles down. So those bond angles won't be exactly 109.5. They're actually going to be slightly less than 109.5. It's going to be about 107. But do note that all of these bonds are identical to one another, right? This is hydrogen, nitrogen, hydrogen, hydrogen, nitrogen, hydrogen. So there's really only one bond angle to report. In this one, there's multiple, so I have to specify which one I want you to report, all right? So hopefully that clarifies it. Obviously this question, and so see here, it's the approximate bond angles if there's more than one present. So here, if I said hydrogen, carbon, hydrogen, you would say less than 120, but if I said oxygen, carbon, hydrogen, it would be slightly more than 120. Okay, all right, so yeah, measuring atoms on scales that us humans can measure. So thinking about it in grams. So there's a couple of conversions that I think you have to memorize. Do I give you Avogadro's number? Can someone check? Do I give it to you? Do I give you 6.022 times 10 to the 23? Yes, no, yes. Oh, okay, perfect. But you need to know what it means. Do I just put Na equals 6.022 times 10 to the 23? So you have to know, no, okay. So you have to know what that means, what that number means. Like if you just remember, it's no use if you just remember 10.022 times 10 to the 23. You have to know what that means. It means that there are that many particles, all right? Particles is equal to what? It's equal to 1 mole. That's the definition of Avogadro's number. It's like saying 1 dozen of something equals 12 particles. It's like the same analogy. It's just instead of 12, when thinking about a dozen, it's just a butt ton. It's 6.022 times 10 to the 23. So the neat thing about mole amounts is we can take the masses off the periodic table and not think about them in AMU anymore. We can think about them in grams. So we use the same exact numbers because chemists are lazy and we don't want a different periodic table to use. We want to use the same thing. So any of those numbers, yes, that we use is a gram amount for moles. So Lauren said the conversion here, you go from grams to moles to molecules. That's absolutely correct. The caveat, though, is molecules as if you're working with a molecule. If we look here at this example, gold. Is gold a molecule, Lauren? Not to put you on the spot. Gold is not a molecule. So instead of molecules, we're going to atoms. So just to be specific there, because this question is asking how many atoms of gold are present, but the calculation is the exact same. So in this example, 1 mole worth of gold, we can kind of think 1 mole of gold in this case equals 6.022 times 10 to the 23 particles, specifically atoms of gold. All right, so that's one of the conversions that we will use here in order to get to specific atoms. But now how can we go from a gram amount to a mole amount? And this is where we use the molar mass of gold from the periodic table. So again, you're always given these numbers, you just need to know how to use them. So gold, and do you know what gold is? It's AU on the periodic table. All right, because I don't give you names. So AU is 197.0. All right, so this is a gram amount. So I like to think about the periodic table. It's grams per mole. Those numbers, that's the unit there. So how we can rewrite this unit is we know that there's 107.0 grams is equal to 1 mole worth of AU. So if you recognize here, this is a derived unit where there's a fraction. So the numerator goes with the number. Whatever units on the denominator gets an implied 1. It's no different than any other from like our GTT example. When you're given units that have a division sign here, whatever units in the denominator gets an implied 1, and it works all the time. And you can get a conversion like this, right? So these are the two conversions we'll use right there. Mole of gold is that many atoms, and then a gram amount is 1 mole of gold. So these are the two conversions that we will use. So start with the piece of information that's given. 4.98 grams of gold is being weighed. So now it's a puzzle, and you just look and see, okay, how can I fit the pieces together to get the unit that I want? So I see right here, I have a gram amount, so I'm going to put that on the bottom. All right, and then write whatever is associated with it on top. So 1 mole of AU. And so if you see the units cancel, grams cancel, now I'm in moles. So now I can use my Avogadro's number, where I put the 1 mole amount on the bottom and 6.022 times 10 to the 23. So do know, and this is the unit of atoms of gold. I urge you to practice using scientific notation on your calculator so you get the right answer. Oftentimes I see students get off by a factor of 10, and it's because they haven't practiced using exponential, putting exponentials into their calculator. So times 10 to the 23. I'll oftentimes see answers off by a factor of 2. And you'll know that I always put that, or a factor of 10. I put that wrong answer on multiple choices as well. Okay, and so if you stick all of that into your calculator, you get a really big number. There's a lot of atoms. There's a lot of atoms there. All right, and so the answer I get, you see it in the key, is 1.52 times 10 to the 23 gold atoms. So a lot of them. Oh no, sorry, it's 22. I think or did my mouth say 22, but I wrote 23. All right, so there we go. Use sig figs for each math problem. Yes. So I reported a reasonable number of sig figs. All right. So I see that all of these are multiplication. All right. So I pick the sig fig with the lowest amount, or the value with the lowest amount. Usually it's the number that's actually measured, the one that's given. So 4.98 has 3 sig figs. It's all multiplication. So my answer should have 3 sig figs in the answer. All right. So there we go. Okay, so this next one, same idea. It's just now we're working with molecules. With gold, we worked with molar mass of just one element, but when we kind of scale up to molecules, it's still applied the same way. We just need to consider, okay, all of the elements, all of the different elements present in a specific molecule. So here I give you the chemical formula of caffeine, and I want the molar mass. Know that that has a unit of grams per mole. And so you just look off of the periodic table and you add up all of the molar masses of the individual atoms there. So you'll do 8 carbons, 10 hydrogens, 4 nitrogens, and 2 oxygens. All right. And so times the molar masses of all of those. So you can see the work that I did there. Okay. And so when you do all the addition of those molar masses off of the periodic table, again, you don't have to memorize these, but I hope by now you know about how much carbon weighs. It's about 12.01. You get, when you add this up, it's 194.19 grams per mole. That's the molar mass of caffeine. All right. And so see that this number, this unit, grams per mole, it's the same unit that we talked about the molar mass of gold. So this will allow us to go from mole amounts of caffeine to gram amounts of caffeine, just like we did for gold. So in this next question, oh, my thing's going slow. Whoops, there it goes. Okay, it's lagging. I just got Starlink like today, because you guys know I live on a farm, and my internet for like the past 2 years has been a cell phone strapped to the roof of my house. That's the only way I can get internet. And I finally, I pre-ordered Starlink from Elon Musk like a year ago. It's like a satellite internet, and it's super fast. Like Elon Musk has been using reusable rocket ships, sending satellites into space. I'm joking. It wasn't a phone on the roof. Okay, so do you see this thing right here? This antenna. That was my old internet. Okay, that thing that's pointing out the window, that's my internet. But now I have Starlink, and so it's a fancier dish that points to like thousands of satellites that are in low orbit satellites that are in outer space, and connect me to the internet. So I just got it today, and it's great, but I lagged a little bit right there. So it's, yeah, yes. And Elon Musk just bought Twitter. So I thank Elon Musk for saving me. I have to, when we watch YouTube videos on our TV, we have to watch it in 480, like 480p. It's so bad. It's like it's just like brown pixels on the screen. It's so bad. You guys don't know how good. That's why I did all my Zoom sessions from school, because that's where the internet was. How far is my commute? It's an hour, but I live in paradise, so that's why I do it. And I love my job, so I make it work. Okay, all right, so there's my thing. So Elon Musk internet, I finally am, I can reach my full capabilities and connect to the internet. You guys don't understand how like awful it is to not have consistent. I can't even get DSL. I don't even know if you know what DSL is. I can't even get it. Like, that's how bad it was. Okay. All right. Sorry. It's getting off track. Okay. Sorry about that. So, moles of caffeine, what does it weigh in grams? So this question's the exact same, pretty much as our gold example. It's actually less steps. So we do recognize that we just got the molar mass of caffeine, how much 1 mole of it weighs. So 194.19 grams per mole. So just recognize, rewriting that as a conversion factor. So 194.19 grams equals 1 mole of caffeine. All right, so this is the conversion that we need to go from what's given, a mole amount, to a gram amount. So this is just a one-stepper. It's kind of two steps. Like if I told you the molecular formula of caffeine, you would have to get this number first, and then use molar mass to convert moles to grams within there. So start with the mole amount of caffeine and just cancel your units. So 1 mole of caffeine is 194.19 grams. All right, and then just plug that into your calculator. What is a reasonable number of sig figs to report here? Reasonable number, 2. Yes, 2 sig figs. Yeah, so whatever that, 74. I think that's the answer. Okay. All right, so that's midterm 1. So let's go on midterm 2. So organic chemistry. So let's look at these molecules and name them. All right. So we typically only name simple organic molecules. So the strategy here, do I write the strategy? No, I don't. Is to find the longest carbon chain, then number the carbons so we can name the substituent. All right, so the substituents that I talk about in this course that we worry about are just alkanes. So like in this example, our longest carbon chain is the ring, actually. The ring is our longest continuous carbon chain. So you see here the substances that aren't named are the carbons that are sticking off. So these are alkane or alkyl substituents. So we have to name them using our naming convention within there. So the first step here is to identify the parent or the parent name, the longest continuous chain. So I see in the ring there's 5 carbons. 5 carbons is pentane. So do memorize those names. But because it's a ring, we call it cyclopentane. So if it was like 1, 2, 3, 4, 5 like that, then we would just call it pentane. But because it's a ring, we call it cyclopentane. So that the parent name cyclopentane goes at the end. All right, so that's the end of the name goes there. Now we have to name the substituents, but we have to be careful. We need to tell the reader where those substituents are on the ring. So you always want to number them so you end up with the lowest numbers in the name. So I'm going to just start right here and name these, number the carbons 1, 2, 3, 4, 5. So we have substituents on carbons 1 and 2. Like you don't want to number it so they're on 3 and 4 or like 4 and 5. Like that's unnecessary. Just start so the numbers are the lowest. And so both of these substituents are 1 carbon. 1 carbon is typically methane. But because these are substituents, we drop the ane ending and we say ol, like YL instead. So these are methyl groups. There's 2 of them, so we call it dimethyl. All right, so this would be 1, 2 dimethyl cyclopentane. All right, actually, I'm not done there. All right, so we have 2 substituents named, but do note that I have the stereochemistry also indicated here, that both of these methyl groups are pointing up on the same side of the ring. So do note that when we look at line structures like the skeleton structures, that there are kind of hidden hydrogens that you don't see. So there's hydrogens on carbons 1 and 2 as well in order for carbon to have 4 bonds on it. So since the 2 substituents are pointing up, this is actually cis 1,2 dimethyl cyclopentane. I hope that you can write or understand what would it look like if it was trans 1,2 dimethyl cyclopentane. It would look the exact same, except one of the substituents would be going down, so it would look like this. Or if we change the numbers, essentially you would just change, okay, where is the substituent, which carbon number is it attached to? Lots of different ways to talk about, think about naming here. Okay, so the question is, will these types of questions be multiple choice or fill in the blank? Mostly multiple choice. So what you have experienced in previous midterm 2. All right. It's not fair to actually have you fill in the blank. What if there were 2 dashes? Oh yeah, so there should be dashes in here. There's probably a dash there. And I think that's the only place where there's a dash. There might be a dash right here. No, I think there's just a dash right there. Oh, what if there were 2 dashes? Oh yeah, that would be, okay, sorry, yes. Now I understand your question. So you were saying if the, okay, that's an awful cyclopentane. Okay. To do cyclopentane. There we go. Okay, so carbons 1 and 2. You were saying, what if it was like this? Okay, that's really bad. This? What would the name be if it were like that? Yes, you tell me. Are the substituents still attached to carbons 1 and 2? Yep, it is. Is it still cyclopentane? Yes, it is. So the question is, okay, well, how about the stereochemistry? Now both of the methyl groups are pointing down, okay? But are they still on the same side? It would still be cis. In this case, since the CH3s are still cis, or sorry, still on the same side, they're just pointing down, it would actually still be cis. So how we go from this picture to this picture is you just put a spatula under the molecule and you flip it. You just flip. Do you see that in your brain? I hope that you can think about that in your brain. Or like just close your eyes and think about taking this molecule and just flipping it upside down, or thinking about it like going under the molecule and looking at it from below. That the two, these 2 methyl groups are still on the same side. So this molecule would be actually named the exact same. It's actually the exact same molecule. You're just looking at it from a different angle, all right, where the molecule's on the same side. Yeah, how can we make an example that's trans? It was this one. So here, if I just take this one, in order to make this trans 1,2 dimethyl whatever, we would have to do this. Okay. All right. Where like if I drew, so there's my eyeball. Okay. If that's the plane of the molecule and there's 2 methyl groups. Okay. There's my eyeball. 2 methyl groups right here. All right. Those are the carbons. Essentially, I'm really exaggerating it, but this would be like the CH3 and the CH3. This would be trans, right? If you were looking at it from the side here, and you would see how these bonds were kind of angled, they would be opposite of one another, so it would be trans. What cis would look like in the first example would be the 2 methyl groups are on the same side. This is cis, versus if we have them pointing down, it's still cis. It's actually the same molecule. We just flipped it like a turtle. Cool. Does that clarify this? If this is a fill in the, there's not going to be a fill in the blank, name a thing. It will typically be a multiple choice. There's just too many, there's like too many places for dashes and commas. The types of questions that you guys have seen on the midterms are similar to what you'll see on the final. Have I ever asked you a fill in the blank, name something? That's not my style. There's just way too many things to include there. All right. So if this was a multiple choice, you bet your bottom dollar that I would have cis option and a trans option within there. Okay. And so a good question is, okay, how is this molecule and this molecule related? Are they structural isomers? Are they conformational isomers? Are they stereoisomers? Are they completely different molecules, or are they the same molecule? If we look at these 2, what type, how are they related? I think how I phrase it on an exam is, how are these 2 molecules related, if related at all? This one and this one. Are they the same molecule? They're not the same molecule because they have different names. And so someone mentioned conformational isomer. Conformational isomers also have the same name. A conformational isomer would be like, okay, this is pentane, but this is also pentane. I just twisted a bond. Yeah. So these are actually stereoisomers because they have cis and trans. They're different within there. All right. What if I had this molecule and the one that I did before? What if I did this? What kind of yeah, so yeah, how are these two? The question is a stereoisomer the same as a structural isomer? No, they're not. They're not the same as a structural isomer. So if we look at these, so let me go back to my original one. So let's go back to looking at cis and trans. The connectivity is the exact same of this molecule and this one. That if you look, like we both have a ring, like 5 carbons in a ring. Both of them have a methyl group attached to carbon 1 and carbon 2. The connectivity is the exact same. What's different is how the bonds are oriented in space. What makes a ring special is that rings can't twist like conformational isomers, like in a long strand like this. They can twist freely, but in rings they can't twist. So we can lock these bonds into place. So that makes them stereoisomers. And not structural isomers. An example of a structural isomer would be 2 molecules that have completely different connectivities, but the same molecular formula. So an example would be like 1, 2, 3, 4, 5, pentene and cyclopentane. So if you write the chemical formulas of both of them, I think both of them are C5H10 or something like that. That looks like 16. H10. They both have the same chemical formula, like count the hydrogens, they're the same. It's just the connectivity is completely different. So that's what a structural isomer is. Same formula, different connectivity. All right. Okay, so let me go back to this example. What if I did these? What kind of, how are these 2 molecules related? So the question is, provide an example where it's trans. It's the one I just had, this one. That is trans. The one on the right here is the trans isomer. Sorry, the trans stereo isomer. How we know it's stereo is because we use the trans cis naming convention here. That's what makes it a stereo isomer. We use cis and trans when it's where how the substituents exist in 3 dimensions matters. And so we use cis and trans. So that this one is your trans isomer. Okay. All right. Come on, guys. I want you to answer this. How are these 2 molecules related? Are they structural isomers? Are they conformational isomers? Are they stereoisomers? Are they different molecules? Are they the same molecules? Okay, yeah, they are. So remember, structural isomers are like these 2. So these 2. So sorry, these 2. These are structural isomers. Same formula, different connectivity. Completely different. These 2 molecules have the same formula, same connectivity, just different, like we just let it wag in 3 dimensions, that we just rotate it a little bit. All right. These 2 molecules. Okay, so we mentioned that they're mirror images. That's true. Then my question is, are those mirror images superimposable? Because if they're mirror images and they're not superimposable, then those are enantiomers, right? We have like a chiral center that your mirror images don't superimpose. But if you take the mirror images of these molecules, they look like mirror images. They actually are superimposable. They are the exact same molecule. Yes, they're the same. They're the same. They're the same molecule. Same molecule, just we're looking at it up from upside down. We just take the molecule, we stick a spatula under it and we just flip it. It's the same molecule. We're just looking at it from a different angle. Okay. What is a conformational isomer? It's when it's the same molecule, but you just rotate the bonds. So see how like this molecule, okay, if I just kind of rotate that bond up, it becomes this molecule. It's the same molecule. They both have the same name. That's a conformational isomer. Okay. So, all right. Can I keep going? All right. All right, let's do this one. Same thing. Let's look for the longest chain. Sometimes, don't try all the routes. And so what I mean by continuous chain, we count the carbons and we want to draw them in a line without lifting our pen at all. I think that's how a student described it. So I see, so I just, it's like a maze. You just kind of count your way and try all of the different routes to see which one's the longest. And so don't always pick the first one that you do. So 1, 2, 3, 4, 5, 6, 7, 8. So that route has 8. I'll do this one. 1, 2, 3, 4, 5, 6, 7, 8. So that route also has 8. But then this last one, if I do 1, 2, 3, 4, 5, 6, 7, 8, 9, that is actually my longest chain. Did everyone else get that? So 9 carbons. That is my parent structure. I know that that is called a nonane. No, I think I spelled that wrong. Nonane. Yeah, nonane. So 9 carbons. And so everything, nonane counts as all those carbons I have in a row here. So now I just need to name the substituents that I haven't highlighted. So this substituent and that substituent. Cool, they're the same. That is 2 carbons, so that would be like ethane, but because it's a substituent, we call it an ethyl group. And because there's 2 of them, we say diethyl. All right, and so now we just need to tell the reader what carbons they're attached to. So what's nice about non-cyclical molecules like this is just number your carbons from one end and then just try it the other way and see if you get smaller numbers. So if I do it this way, one of the substituents is on 4, the other one is on carbon 6. And if I do it the other way, 1, 2, 3, 4, 5, it's the same. So it's 4 and 6. So this would be called 4, 6 diethyl nonane. Cool. Okay. There we go. All right. One more. All right. Ooh, yay, another cyclical one. Okay. So hopefully you see there's the parent, it's the ring. So this is cyclopentane again. Okay, cyclopentane, yay. Pentane, because there's 5 carbons. Now we just named the substituents. So there's a carbon there, there's 2 carbons there, and there's a carbon there. So there's 2 different methyl groups. So this is dimethyl, because there's 2 of them. So we don't have to say methyl. And this group is an ethyl group. Right? So make sure when you name this, typically, again, we want the numbering to be the lowest, and with rings, it's a little bit harder. Oh, my connection is unstable. Okay, let's just keep going. So when it's a ring like this, still number it the lowest possible. Typically, we want to place the substituents in alphabetical order if there's more than one that have different names. So I want to put the ethyl group first. So I'm going to just make that one carbon number 1. So it comes first in naming. And then I'll just kind of count both ways and see which one gives me the lower number. So 2, 3, and 4. So 2 and 4, or if I count the other way, it would be 3 and 6. So I want to do it the first way. So I'm going to name it 1, 2, 3, 4 in that case. So this will be called 1 ethyl, 2, 4 dimethyl cyclopentane. Cool. There we go. All right. So that's naming. All right. So 17. I like these ones. Let's write the chemical formulas for these. So a question maybe, will we have to name these? Oh no. You don't know how to name these. I won't make you name those, but what you can do is come up with a chemical formula, and you should be able to identify any functional groups that are present. Like right off the bat, I see there's an alcohol group. Here's an alkene. It's a double bond. And this guy is a carbonyl, but what type of functional group is it? I always, when I memorize my functional group, there's kind of two schools of thought. There's the carbonyl containing functional groups, the amides, the ketones, the aldehydes, the carboxylic acids, the esters, and then there's like all the things that don't have a C double bond O. Yeah, so this functional group is a ketone because off of the carbonyl carbon, there's two carbons, two R groups. When off of your carbonyl carbon, there's a hydrogen, that's called an aldehyde. When it's an OH group, it is a carboxylic acid. When it's an O minus, it's a carboxylate, which is a carboxylic acid without an H plus. Which one did I not do? If it's an OR, so like an oxygen, but an R group instead of a hydrogen, that's an ester. And what's the last one? Amide is when it's a nitrogen off of the carbonyl. So that's how I think of those. Yeah, so that is a ketone. All right. And then we have an alcohol here, but what kind of alcohol? Do we have this? Is there a special name for this alcohol? What makes this alcohol different from what if I had an alcohol like right here? Or if I had an alcohol like here? Yeah, so this is a secondary alcohol because the carbon it's attached to is attached to two other carbons. This one that I made up right here, this would be a tertiary alcohol because the carbon it's that alcohol is attached to three other carbons. This alcohol is a primary because the carbon it's attached to is attached to only one other carbon. So that's how you determine those. Okay, so there's the functional groups. Very good. That's basically it. We don't count alkanes. The alkanes are there, but typically that's not one that you count. I will say if there is a name, what are the functional groups in the molecule, it's going to be a select all question. Select all that apply. All right. And there was questions about how select all questions are graded. You are penalized if you select too many. So yeah, so do you understand that? Okay. All right. So let's get the chemical formula. So how the heck do we do that? We need to recognize how to read line structures, that every single point here of these lines is a carbon. So we should be able to figure out how many carbons are here. Do I have my strategy? Yeah, count carbons and count heteroatoms, meaning, okay, I hope you can see that there's two oxygens here and all the other kind of like points in our line structure are carbons. So let's go and get those carbons. So there's a carbon there, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So there are 20 carbons. All right, and then there's two oxygens. Okay, so now the hard part is getting hydrogens. How the heck do we get hydrogens? We have to recognize the rule with carbons. Carbons always need 4 bonds. So if based on this line structure, we should be able to know how many hydrogens are attached to each carbon based upon how many bonds are already there. So for example, this carbonyl carbon, it already has a double bond here and 2 single bonds. There are no hydrogens attached to that carbon. But if we go next door, this carbon only has 2 bonds drawn. These are like what I call invisible hydrogens, the hidden hydrogens. Oh no, it's being slow again. These are your hidden hydrogens. There's 2 hydrogens on that carbon atom. So you have to do this with every single carbon and see, okay, how many hydrogens do I need to ensure that that carbon has enough bonds there? So we'll do all of them. So there's 2 there. This carbon's a little bit tricky because there's a double bond here and a single bond there. So that's a total of 3. So there's actually only 1 hydrogen there. If we look at this carbon, there's 1, 2, 3, 4. So there's actually no hydrogens on this carbon. And there's also no hydrogens on this carbon either because it already has 4 bonds. But this carbon has 2. All right. This carbon has 3. Did you count 19? Oh, is there 19? What did I double count? Did I cut? My key also says 19. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Yeah, I don't know why I said 20. I only have 19 dots. Thank you. Okay. Always double check. Double check. Okay. But the hard part, if you're gonna get this wrong, it's the hydrogens. So yeah, so this carbon, I trust me that I this carbon has okay, come on. My screen's come on. This carbon, oh yes, is has 3 hydrogens because it's on the end here. It's only attached to one other carbon. And so let's just keep going. This one has 2, 2, 1, 1, 2, 2, 0, 3, 1, 2, 2, and 1. So hopefully you got that, all of those. And then just make sure, double check that everything has a, every carbon has 4 bonds there. And so if you count these, let's see if I can count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Count this one, that hydrogen. 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. 28? Yes, that's what my key says, 28. So C19O2H28. So pick the answer that has those ratio of atoms. So this is tough. This is tough. But my strategy: find the count the carbons and the heteroatoms. You know how to read line structures, and then you need to find the hidden hydrogens. So this one we should be able to do too. So carbons first. 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is C9. Now count the heteroatoms. What I mean by heteroatom, it's an atoms that aren't carbon or hydrogen. So I see that the only other like weird elements is oxygen, and there's 3 of them. Now it's the hard part, it's the hydrogens. So benzene here, this ring, all of these carbons have a single bond and a double bond. So I'm going to draw the hydrogens as green lines. So there's hydrogens there. There are no hydrogens on these carbons because they already have bonds to other atoms. No hydrogens here. And then there's 3 hydrogens here, and then there's 1 hydrogen there. So 1, 2, 3, 4, 5, 6, 7, 8, 8. Yes, that's what my key says, H8. So that's the chemical formula. So 4 oxygens. Yes, there are 4 oxygens. So embarrassing. Yes, there are 4 oxygens, but I got the rest right, right? Okay, good. Keep me on my toes. All right, let's keep going. All right, let's just do one more. We'll do this one a little bit quicker. I'll probably get it wrong. So carbons first. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. C18. 18, you struggle with adding. Yeah, I have to check 2 plus 2 in my calculator. C18, that's what my key says. Great. Now heteroatoms, be careful. Okay, there's 1 oxygen, right? 1 oxygen, 1. Nitrogen is also a heteroatom. There's 2 of them. That's it. That's it. Yes, so 2 nitrogens. Okay, now it's the hydrogens. That's the hard part. Do remember there's a hydrogen right there. There's a hydrogen right there. So 1, 2, 3. There's no hydrogens there. 4, 5, 6, 7, 8, 9, 10. This one's 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. H28. Okay, that's what my key says. So there we go. All right. So again, the hard part is the hydrogens because they're hidden. All right. And do be careful with benzene. Okay, because those carbons, you know, they have a double bond and a single bond. So if there's a part of your benzene or your aromatic ring there's one hydrogen, but if there's already a bond here, then there's no hydrogens on that carbon atom. Oh, we didn't do functional groups. Okay, I'm going to delete this real quick and we'll just look at functional groups. Okay, so right off the bat, I already called it. This is an aromatic. Okay, that's an aromatic group. It's a benzene group. We call it aromatic. Aromatic. Something that looks like an aromatic, but we don't call it that, is if there's an OH group attached to it. So we don't call, if you see something like this, don't call this an aromatic and an alcohol. Those two add together and we call it something specific. We call it a phenol group. Phenol group if it's an aromatic attached to an OH, right? We call it a phenol. So it's a special name, but that's not what it is. Okay, it's aromatic. Now we have this nitrogen group. Do recognize if there is an adjacent carbonyl to it. So there's that nitrogen group. It is adjacent to a carbonyl carbon. So this is not an amine, it is an amide. And you know for a fact that I will have the option of amide and amine on as a select all. So this is called an amide. It is not called an amine and a ketone. That's oftentimes what students will say. So when your nitrogen, your like amine group is attached to a carbonyl, like adjacent to it, we call it an amide instead. But this group, because it's a nitrogen not adjacent to a carbonyl, this is called an amine. Okay, because it's a nitrogen, no adjacent carbonyl. All right. This ring, we don't have a name for it, so you don't have to name anything else because they're all single bonds within there. Let's go to the previous one that I missed. Okay, so there we go. All right. So looking at the groups, here is another aromatic. Okay, I don't see an alcohol attached to it, so I don't have to call it a phenol. We just call it an aromatic. All right. This group is a carboxylic acid. And this group, so see how we have a carbonyl and an oxygen, but because the oxygen isn't attached to a hydrogen like it is on a carboxylic acid, we call this an ester instead. Ester. So amide has a double bond, amide has single bond. No, that's not quite the case. A amide has a carbonyl, a carbon that is double bonded to an oxygen. That is called an amide. So it looks like this. So like that's your carbonyl carbon. You always look at what is attached to that carbonyl. If it's a nitrogen, it's an amide. When it's an OH, it's a carboxylic acid. When it's an OR, it's an ester. When it's just a hydrogen, it's an aldehyde. When it's another carbon and there's a carbon on the other side, it's a ketone. So do go back to those functional groups and review those. Ester and acetyl, don't worry about acetyl. Don't worry about acetyl. Just call this an ester. This is technically called an acetyl, but just call it an ester. It's fine. Acetyl is a special type of ester, but I don't want to go into the details of that. Okay, did we do all of them? Yes, we did all of them. Ester, All right, so there's no ether. That is correct. There is no ether. Yeah, exactly. So here I called this one an ester. All right, so what the common mistake would be is students will recognize, oh, look, there's an oxygen in the middle of something. They might call this a ether and a ketone, but that's not correct. When you have that oxygen adjacent to a carbonyl, it's now called an ester instead. So it's not an ether and a ketone, it's an ester instead. But if they are far away from one another, then yes, you'll have an ester. Like if you have something like I don't know, like an oxygen over here, and then like this or something. Yes, this is an ether and this I guess would be a aldehyde or something. They are very far away from one another, so you can count them separately, but it's when they're right next to one another, then you would call it an ester instead. Cool. Yeah, so if we like brought this closer, all right, like that, Now it would be called an ester instead of an ether and like a ketone or an aldehyde or something like that. All right. So, all right, good. All right. Okay. How many moles of carbon dioxide will result from the complete combustion of this molecule? So as you know, I can't on a multiple choice exam or on Carmen, I can't ask you to draw a molecule. So this is the best I can do is I tell you, okay, you have a combustion reaction. And you burn this molecule and I give you a name. Because when we think about a combustion reaction, our products are CO2 and water. How we get the number of moles of CO2 that are produced is if you have the correct chemical formula of your molecule. So given the name, you have to first draw the structure and then do what we were doing up here and get the chemical formula. So this question 18 is kind of a two-stepper. There's a lot that you have to do here. We need to take this name, cis-1,2-dimethyl-cyclohexane. We need to draw it. So we're working backwards here. I like to identify the parent structure first. So cyclohexane, hex means 6. I need to put it in a ring. So this is cyclohexane right there, right? And now I need to name the substituent. So it's dimethyl, and I say that it's on carbons 1 and 2. So I'll just put them here, dimethyl. And I say that they are cis. So to make them cis, I'll just make them both go up. But we talked about this before. We can also make them both go down. And we would have dimethyl. So this is CH3, right? Like that. All right. And there's your molecule. Okay. Since we're just getting the chemical formula, we actually don't need to, we don't really care about the stereochemistry. If I called this trans dimethyl cyclohexane, the answer would be the same because they actually have the same chemical formula. All right, so we need to get the chemical formula. So it's the same idea. We need to count the number of carbons, 1, 2, 3, 4, 5, 6, 7, 8. There's 8 carbons. And then we can get the number of hydrogens. Well, actually, we don't need the number of hydrogens here since we just need moles of CO2, but let's just do this for completeness. So hydrogens, there's 2 on all of these carbons. So 8, 9, 10, 11, 12, 13, 14, 15, 16. There should be 16 hydrogens. So there's my chemical formula. All right. And so combustion reactions, we're taking oxygen and making CO2 and water. So we don't really need to balance the whole equation. We just need to figure out how many moles of CO2 we produce. So in this question, all of the carbon is coming from the molecule itself. So there has to be 8 CO2s in order for this combustion reaction to be balanced within there. So the answer here would be 8. So this is how I get around asking you to draw something, because if you draw this incorrectly, you'll get the wrong number of carbons. You'll not be able to get this answer if you can't draw it, right? So this is kind of how I get around it. Can you draw and get a chemical formula out of this? I could also ask you, I think this was on one of your exams, what is the sum of moles of CO2 and water produced? So we could take this one step further and balance H2Os. So recognize that all of the hydrogens from your molecule that we got the full chemical formula is going towards water. So you just figure out, okay, how do I balance that? There has to be 8 H2Os as well. So the sum here would be 16 if the question asked moles of CO2 and water. So do recognize that you would need the number of hydrogens in your molecule as well. All right, so we could have just stopped by the number of carbons and we'd be done. We wouldn't have to get hydrogens, but just for completeness, we'll do all of it. All right, so keep going. How much do we have? Oh crap, we have a lot more. All right, should we just keep going? Keep going. 19. Okay, unless someone, we have about 25 minutes left. So if there's a certain question you want me to go over, just throw it up in the chat, but I'm just gonna keep going. Okay, so which of the following monosaccharides is aldopentose? So this we're away from chapter 4. This is carbohydrates, where we recognize we draw these Fisher projections on drawing sugars, and that each of these carbons that are in the cross are chiral centers, that the position of that OH, is it on the left or the right, matters based upon the stereochemistry. So these 3 carbons are chiral. This sugar only has 2 chiral carbons. This one has 1, 2, 3, 4, because like this carbon, if you look at all of the groups attached to it, they're all unique, they're all different. So that carbon is chiral, but the carbons on like the ends are not chiral, because either they're not there's not 4 bonds, there might be a double bond present, or 2 of the bonds are the same. So here on this end, see how there's C and 2 hydrogens and an OH. So since there's 2 hydrogens, that end can't be chiral. So this question is saying classifying monosaccharides by their name here, aldopentose. Pent tells you how many carbons are in the sugar. Aldo tells you what type of sugar it is. Is it an aldehyde or a ketone? So A and C, yes, are both aldehyde sugars, while B and D are both ketone sugars, because you can see the functional group here, we have ketones, and here, this is just a different way to show an aldehyde. So I think the answer is, it has to be A or C. So we need one that has 5 carbons. So 1, 2, 3, 4, 5, 6. Nope, that's an aldohexose. Our answer is A, 1, 2, 3, 4. Yeah, 5. So aldopentose. Okay, so question, can we do 28? Unless we did it in class. Okay, 28. Okay, yeah, so let's look at these other functional groups. Which of these compounds are most likely to be soluble in water? So recall water, H2O. If we just had a pure sample of water, and if we looked at its Lewis structure, we already drew this today. Okay, water is polar. It can participate in dipole-dipole interactions, but it can also participate in hydrogen bonding. So this is a question about intermolecular forces. When things are soluble in water or in any solvent, it just means that their intermolecular forces match. So you need to ask yourself, if you had a bunch of water and you added one of these compounds, does this compound make strong attractions with water or weak attractions with water? We know hydrogen bonding is really strong, right? So this molecule, we have 2 different sources of groups that can hydrogen bond. So recall the criteria for hydrogen bonding. You need either an OH group, an NH group, or a HF group with a lone pair on the electronegative atom. Those types of molecules can hydrogen bond. So here we have 2 sources of hydrogen bonding. So this one is the most soluble, versus this one only has 1 source of hydrogen bonding. This molecule has 0 sources of hydrogen bonding. Okay, so of these, this molecule is going to be the least soluble in water because there's no hydrogen bonding, but there is dipole-dipole attraction. So this molecule probably will be a little bit soluble in water, but not as much as this molecule, because it can make really, really strong attractions. With water, they will mesh and be very attracted towards one another. Therefore, they will mix together. So when looking at questions like 28, you want to look for matching intermolecular forces. So I could easily change the solvent. Instead of water, I could change it to some type of non-polar solvent. And so when we're looking at non-polar solvents, you want to also look for non-polar solutes to dissolve it in. So essentially our answers would be backwards if our solvent was like hexane or something. If it was like C6H14 hexane, the answer would be different, because you would want more non-polar compounds to dissolve in a non-polar solvent. This is superpolar. It is, yeah, superpolar, can hydrogen bond. That doesn't mesh well with a non-polar solvent like hexane. So that's a similar type of question. For hexane, I wouldn't use these examples. I would use things that were more non-polar, like CF4, CH2, F2, or something like that. And I'd ask you, okay, which of these would be more soluble in hexane? it would be this one because it's nonpolar if you draw out the Lewis structure. All right, can we do another chiral question? Let's look at, yeah, let's do a chiral question. Let's see, chiral question. I don't know. So if we go back to this question, the 19, I could ask you, okay, how many carbons are chiral? And again, you would look for carbon atoms that have 4 different things attached to it. Different things. So in this case, A has 3 chiral carbons. This one has 2, 4, and 3 in this last one. So you have to kind of look at every carbon individually and look and see, okay, what's around it? Is it different? And that will tell you if it's chiral or not. Let's look at like this. I don't think there's any chiral centers. No, there's one. There's a chiral center here, and you can tell because there's stereochemistry indicated there. I don't know if there's other ones I can really point to right now, but the big idea with chiral carbons is you need to look at everyone individually. Anyone that has 4 different bonds to it. So like in this example, you don't have to look at any of these carbons that have double bonds on them. They will never be chiral. You have to have 4 different bonds to it. So really, there's no chiral carbons on this molecule because the only carbon with 4 bonds on it is this, or 4 different things attached to it would be this carbon, but there's 3 hydrogens. So there's identical atoms there. Okay, when looking at the ring structure of a carbohydrate, how do we determine D or L? That's not a learning objective of this class. So how a D or L question would be asked, it's too complex. Basically, that's what I'm trying to say. It would be like this question. I would say, okay, which ones are D and L? And so recognize how we indicate D or L is when we are looking at the line, not the ring form of a sugar. And we are looking at the last chiral carbon of our Fisher projection here. So we're looking at the last one. Last chiral. We don't look at the tail because these carbons are not chiral. We're looking at the last one. So all of these are D isomers because the right D right, yeah. The OH group is on the right side of the molecule. Okay, so I'm gonna go to 30 because that was asked, and then okay, so more math here. So just get down with units and you'll be good. All right. But know what molarity means and what that unit means. So we have a solution of ammonia and it contains 4.25 grams of NH3, that's ammonia, in this much solution. What is the molarity of ammonia? So recognize that molarity, the unit is moles of your solute. So in this case, it's NH3 because that's what we care about, over liters of your solution. So look at the information given and see, okay, how can I get to that, get these different quantities and divide them? And that's what's going to get me molarity. So looking at this, liters of solution, oh, they give me a volume right there. So there it is. The only problem, it's in milliliters. So 515 milliliters is 0.550 liters. So that's given. We already have the denominator. We're halfway there. We just need to get moles of NH3. And then if we just divide those numbers, we'll get it. So I don't give you moles of ammonia, I give you grams of ammonia. So this question is just like the gold question we did before. And look, I even give you the molar mass of ammonia because I'm super nice. So recognize molar mass means how that's written, 17.03 grams of NH3 equals 1 mole of NH3. So if I start with 4.25 grams of NH3, I just use the molar mass, make sure those units cancel. So I'm putting 17.03 on the bottom and 1 mole up top, and that will give me my numerator number. So if you calculate that, you get something, small number, 0.0 2496. This would round to 3 sig figs because this has 3 sig figs, but I'm not done. So what I would typically do is just leave this in my calculator and then do the next step, which is divide it by liters to finish off this equation, moles over liters. And so I'm just dividing by 0.550 liters, and that will give me molarity. It's 0.454, 3 sig figs here because everything has 3. Okay, so that is 30. Okay, so let's do 32, similar, it's using molarity again. So recognize molarity means moles over liters. So I am, oh wait, this is a dilution question. Okay, so we are calculating the molarity of a solution diluting 255 milliliters of NaCl to a total volume of that. So we're changing the molarity. The molarity is going to go down. The concentration is going to go down. Molarity is a unit of concentration. So we use the equation C1V1 equals C2V2, where C is concentration. It doesn't matter what unit it is in, as long as they match. So I could give you concentrations in molarity. I could give it to you in like percent volume or something, or percent mass, it doesn't matter, as long as the units are the same. Same thing with volumes. We need to make sure that they match. So what we see here, I give one in milliliters, the other in liters. So just make sure that they match in the equation, and it's just plug and chug. So 255, that's how much we're starting with because we're diluting to a bigger volume. So this is V1, this is C1, and 1.5 liters is V2. So we're calculating for C2. So when I plug this in, just make sure that your volume units match. So this is going to be 0.75 molarity times V1. I'm just going to put that into liters. So 255 liters equals C2. That's what I'm calculating, and times 1.5 liters. All right, and C2 will have the unit of molarity, and the answer I give is 0.468. 3 sig figs is sufficient. Everything has 3. All right. Okay. All right. We'll do 31 as well. Okay. So let's back up a little bit here. All right. So what is the concentration, mass percent, by preparing 25 grams of water in 45 grams of ethanol? So to calculate concentration by mass, we take the mass of the solute, so whatever is in the smaller concentration. So note that the unit here, it's mass over mass. So we make sure that the units on the numerator and denominator are both mass. I give you masses, so that's good. Mass of your solute, and then you want to divide that by the mass of your solution and multiply by 100 to make it a percent. But the key here is that the mass of the solution, like if I dissolved like salt and water, the mass of the salt water solution will be the mass of the salt and the water that I combine. So your mass of your solution is the mass of your solute and your solvent together. That's the total amount that's in your beaker when you mix these things together. So when you do this, mass of your solute, that's H2O because it's in the lesser amount, and ethanol is your solvent because there's more of it. So you're going to do 25 grams over 25 plus 45 in the denominator, and then times 100, whatever that is. What is it? 36%. Sorry, my key looks weird. I think I missed the box. So 36% mass over mass is your answer. It is not. The common mistake is that students will just do 25 over 45. If you do that, you're just doing solute over solvent, not solute over solution. And that's true if it's mass percent, if it's mass over volume percent, if it's volume over volume percent, it doesn't matter. It's always solute over solution, not solute over solvent. That's a common mistake, all right? That like 25 over 45. So you know, if that's a multiple choice, you know that that's going to be an option. So you have to do 25 over the sum, 25 over 45. Okay, so there we go. Okay, let me go back to some of these questions. What did it say? Okay. Are irreversible inhibitors different. They're different. Look at the overview sheets about how we differentiate our different inhibitors. There are different ways we can differentiate them. It's based upon their mode of action on how they deactivate the enzyme. Okay, if there are concepts not on your practice exam, is it safe to say they won't be on the final? I made sure, I wouldn't say the practice exam. I made sure that every question that's on the final is on that really long 90 question practice set. I made sure that the exam had one representative question, at least one, on that practice set. So yeah, okay. Okay, did we do 33? No, 33 and 34. We did 31. Didn't we do 31? We did 31. Scroll down. You guys have the key. You already have the key. Okay, so 34. 33. Okay, we'll do 33 and 34. Okay. So 33. Okay, so still solution chemistry, we're talking about equilibrium and how we can shift equilibrium around and how we can change equilibrium based upon Le Chatelier's principle. So this is all based upon the idea of K, our equilibrium constant, and how we come up with that. So how we come up with an equilibrium constant, first we need the balanced chemical equation, where we take the products, right, the concentration of the products to the subscript of whatever is in the balanced chemical formula, the coefficients in the balanced chemical formula, and we divide by the concentration of the reactants. So make sure that your coefficients becomes superscripts, become exponents within there. So if we look at this question, I give you a bunch of concentrations, and I want you to calculate, okay, how much A is present at equilibrium? So I give you the K constant. So K will be satisfied when all the concentrations are of amounts to give K. So if we put together our K equilibrium expression, we take the concentrations of our products, they're both gases. So do not include liquids or solids, but you do include aqueous and gases in your K, but don't include liquids or solids. So K in this case is the concentration of C to a superscript 1, which is the same number, times the concentration of D over the concentration of A squared, because there's a coefficient there of 2, and then times B. All right, and this is all equal to 52.0. All right, so now let's plug in the numbers that we were actually given. So it's 0.742. So do note that K is unitless. All right, so I'm just going to drop the concentrations here. So times D, so 1.22 molarity there. I'll back up a little bit. Okay. We are calculating A. So obviously you're not given A. So that's what we're calculating. So A squared times the B value, 0.553. So what I would do is just bring A over here and bring the 52 over here, but it's A squared. So you have to take the square root of everything. So you would get A equals the square root of like all of those numbers, the same ones, and the 52 down here, it's the same numbers, and that would be the concentration. And so you see it on the key. Will we be able to look through the homework? I had to close them so that you guys can't keep doing late homework. I don't know how to reopen them. I'm sorry. So I don't think you can. So do know that a lot of those homework questions, a lot of them come from the book. So I'm sorry, I don't know how to reopen them without reopening students to do late homework. And I just can't have that happen. I'm sorry. All right, so 33. Let's do 34. So here's a more conceptual idea of our K equilibrium. So if we go back to this question, K, we get this number when we are at equilibrium and actually measure the concentrations of all the species there. So what we're doing in 34 is we're saying, okay, what if we disrupt the concentrations in here? Like, what if we remove some A in the reaction? What happens is that the calculation of K changes. So in order for the reaction to get back to K, to get back to 52, we have to adjust the reaction. So often what happens is that we know if we take away some A, all right, A is a reactant, that the reaction has to kind of fill up the void of A, and that's how we get back to 52. So that's essentially what Le Chatelier's principle is. So in this question, I give you a balanced chemical reaction. I tell you it's endothermic. Excuse me. So you have to figure out on what side of the reaction is heat. Is heat a product, or is heat a reactant when it's endothermic? So for endothermic, it means heat is a reactant. So this is how we adjust the reaction when we add or decrease, add or remove like heat in a sense. So which ones shift to the right? I guess I like to just do all of them. All right. And see how the equilibrium changes based upon if we add or remove substances. So if we add more water, we're adding more reactant. So I like to think, okay, if we add more of that, the reaction is going to go forward. It's going to go in the forward reaction. We're giving more fuel to send it forward. So in that case, the reaction is going to go to the right. If we decrease the temperature, we are removing heat. So if we remove heat, the reaction is going to try to, backfill that void there. So this reaction is going to go left if we decrease or remove temperature. So you can treat heat as just like a normal reactant here, as long as you recognize what kind of reaction it is. If I don't give you it's endo or exothermic, you can't predict it. You have to know whether heat is a product or a reactant. Okay, decrease chlorine gas. Whoops, keep that. Decrease chlorine gas. So we're removing chlorine. So it's the same idea. To fill the void of chlorine, the reaction has to go back to reactants. It's the same thing would happen if we decrease the heat. If we increase temperature, reaction's going to go right because we add more heats, pushing it forward. Increase oxygen. Oops, crap, what did I do? Increase temperature, right? Increase oxygen. Okay, yeah, increase oxygen. So we're adding more product here. So the reaction is also going to go to the left, back to the reactants. All right, because we're adding more products in this case. If we decrease HCl right here, so we're removing products. If we remove products, the reaction is going to try to fill more products to make up for it. So it's going to go right. So I guess our answers are these ones. I hope I'm right. Am I right? I don't know. Okay, so there we go. Okay, what if one was a solid? That's a good question. Yeah, what if one was a solid? Is a solid in the equilibrium? No, it's not. So would it change the equilibrium if we added more solid? No, it wouldn't. So if I had a solid here, and I said, oh, add more carbon, it actually wouldn't change anything. So that's a trick question, right? It wouldn't change anything. If it was solid or if it was a liquid, then it wouldn't change the equilibrium at all because it's not included in K. Because really what we're doing when we are adding these things and, predicting which way it shifts, what we're taking advantage of and looking at is how are we changing K? But since solids and liquids aren't included in K, we're not disrupting this equilibrium at all. Same idea. Another thing is, what if we add a catalyst to this? How does the equilibrium change? It doesn't change the equilibrium. A catalyst changes what in a chemical reaction? What does it change? A catalyst. Yes, it changes the speed. Why does it change the speed? Or the rate of a reaction. It makes the reaction go faster, but in this case, since it's reversible, it makes the forward and the reverse go faster. It lowers the activation energy. Yeah, and that's what we talked about in chapter, I forget, proteins, where we talked about enzymes. Enzymes are catalysts, and how they operate is by lowering the activation energy of chemical reactions in our body to make them go. All right, I have 2 minutes. I can talk through 38. Oh, we already did 38. We did in class. All right, so I'm gonna end there. What if we change pressure? Okay, let's see. So yeah, that's a good question. So if we go back here, if we change pressure, so if I increase the pressure of the system, the reaction will try to relieve the pressure so it goes back to normal. So I like to just count the number of moles of gas on each side. So on the reactant side, there are 4 moles of gas. On the product side, there's 5 moles of gas. So if I increase the pressure, the reaction is going to go in the direction that relieves some pressure. So it's going to go towards the reactants. That's a good question. I think there was a question in the overview sheets about that. All right, so I'm going to end it there. Good luck, everyone. Yes, I will enjoy my evening. I'm going to enjoy really high quality YouTube streaming for the first time in my life. All right. Bye, guys. I'll post, and I can post it like at a reasonable time. It won't take me 50 minutes to upload a video. Huzzah, yes. Our questions on the final directly from the question bank, I don't know what that means. Yes, I don't know what that means. I wrote the exam. So, oh, from the problem set? No, they're not. I wrote the exam. Okay. Good night, everyone. Good luck. Good luck on all of your finals. Goodbye.